Welcome to the lecture series on Similarity Modeling 1 and 2, Seeing and Hearing in Computers. My name is Horst Eidenberger. This short lecture is about evaluation of how you can actually judge how good the quality of a certain algorithm is, a classification, plus of course influenced by the feature engineering. And we have the following educational goals. I want to understand you what a confusion matrix is. It is the centerpiece. It's the pivotal point around which everything rotates in evaluation. Okay. Furthermore, I want you to have a set of measures available, including recall, precision, fallout, more advanced things such as mean average precision and the F1 measure. And I also want you to understand the visualizations, in particular receiver operating characteristics curves and recall precision graphs. With that, you should be able not just to complete your lab task, but you should be able to understand and quickly grasp the meaning of every relevant classification methods and media understanding methods more generally that we have in the field. So let's go directly into the process. We said that similarity modeling is what we do. That means we model first some input data, some vector of description, either consciously in feature engineering or subconsciously or non-consciously in deep networks. And through a classification step, we arrive at the judgment of an output, which is usually a class label, meaning that something is either relevant or irrelevant semantically. That is a process of semantic enrichment. Okay, if you have questions on that point, please watch the video on classification and or ask questions, state questions in the forum, get in touch with your lecturer and your colleagues. Okay, we said that learning requires us to provide an enormous amount of data, depending on the task. If it is a complex task, of course, it is enormous, so we need a media database that contains, on one hand, samples. If it's about speech recognition, it's necessary audio samples. If it's about face recognition, it's images. And if it's about feature film analysis, for example, recognizing action events, then it's a database of video files. Furthermore, for most methods, those that are not unsupervised, we need a ground truth. At the appropriate place in the lecture on classification, I stated that assembling a good ground truth is a very complex and most of the time very costly process that is non-trivial and still, even if you invest a lot of money, it might not be possible to represent all classes to the degree that they should be represented with all their various dimensions. Anyway, it's a different problem. For the evaluation of classifiers, unsupervised or supervised, we always need the ground truth, because the ground truth is the fundamental measurement stick for the quality of the classifier, apparently. And what you compute then first is a twofold matrix which has 4 elements and 2 dimensions. One dimension is the output of your classifier. And the other dimension is the ground truth. And in that matrix, we have 4 essential options for the individual act of classification. And the options are that the output of the classifier and the ground truth are actually the same. So the class labels are the same. In this case, we speak of a true positive. That means your classifier estimates that something, some input, is relevant to some category, to some semantic meaning, it is positive and it is true because the ground truth says the same. If the output of the classifier says that something is irrelevant and the ground truth also says that, then we have a true negative. So it's about classification of relevant into relevant or non-relevant. If you classify a category as something as relevant, but the ground truth says it is not relevant, then we actually have a false positive. And if you claim that something, or your classifier claims that something is irrelevant, however in practice it would be relevant, then we have a so-called false negative. So here we have positive, here we have positive, and here we have negative, whatever that means. Negative certainly 0, positive probably 1, yeah. So that's what it is. And that matrix is referred to as the confusion matrix. In that matrix, true positives and true negatives are the two desired fields. However, these desired results might be confused in two possible ways: the error of the first kind and of the second type. Recognizing something that is relevant as non-relevant is a false negative, and recognizing something as relevant that in matter of fact is not is a false positive. Okay, 0. Good. Of course, the amount of such errors defines the quality of the classification algorithm. So what you always do when you do evaluation, the first thing is, after the training with your training set, you employ your test set in order to check for a certain parameterization, and in the event you use your validation set in order to test the overall approach. These come from the ground truth database. Okay. Thus forming such a confusion matrix. From that we can derive certain statistical indicators. The recall is most important. Is the same as the true positives rate. And that is defined as the number of true positives divided by the true positives plus the false negatives. That means we have a number of relevant categories, relevant items in our database. Some of them are correctly recognized. Others, unfortunately, are not. They are said to be negatives, but they are not. They are false negatives. So they also belong to that category. If that value goes to 0, it means that we are not recognizing anything. If it goes to 1, it means that we recognize everything correctly, which is very good. The recall is certainly the most relevant measure, because after all, what you want from such a system is to recognize what is relevant. A second measure is the false positives rate. Or the fallout. Which is defined as the false positives divided by the false positives plus the true negatives. That means with the fallout we define the output of a classification step over the entire database and how many of those elements are actually irrelevant. So what is undesired? To what extent is the output of the classification polluted, if you want. That is the false positives rate, which gives you also an indication of the quality. You might have in a system a very high recall. You recall everything that is relevant, but unfortunately your false positives rate is also very high. That means that even though you have all the relevance, it's highly polluted. You don't find them anymore in the original data. So what you desire is a false positives rate, a fallout that goes to 0, while the recall remains at 1. The third measure that we have is called precision. Precision is the true positives by the false positives plus the true positives. It is another measure for pollution that has a big advantage over the other two. The big advantage is that it can be computed not from the entire database, but in a retrieval scenario just from the output of the classifier. Because all you need is the true positives plus the false positives. The positives are, of course, the output of the classifier. So it can be computed quite quickly. And it is related to the false positives. That means it should also go towards 0. If it doesn't, you have a problem. You can always achieve a precision of 1, it should go to 1, not to 0. That means that there should be only relevant elements in the output. You can always achieve a precision of 1 by being super restrictive, by having a recall of 0. But that's, of course, not desirable. On the other hand, you can also have a perfect recall while giving up any form of precision. As I said, with the false positives rate, if you just return everything as a classifier, classify everything as relevant, your recall will always be 100%, but that is not desirable. Okay, so much for the simple indicators that are based on the confusion matrix. The next thing that we want to have a look is how we can visualize these measures. There are essentially two forms of graphs. One being the recall precision graph, and the other one being the receiver operating characteristics, or ROC curve, long name. So let's have a look at what they show. The recall and precision graph usually shows the recall here in the top dimension and the precision here. The receiver operating characteristics usually show the false positives rate here, or the fallout, and the true positives rate here, or the recall. Okay. The desired curves are for a recall and precision graph to be as far out as possible. Both of them go to limits of 1, starting at the origin. That is equally true for the rock. And the further out you manage to get, something like that, for example, is completely undesirable in a classifier, the better it is. Very often deep learning methods today for object recognition, visual object recognition, reach a position here or even further out. Okay, that is a good recall precision graph. So if you see a paper and there are recall precision graphs, you don't even have to understand or remember anymore what recall and precision by definition mean, nor you do have to understand what the confusion matrix actually expressed. All you have to do is look at the curve. The further out it goes, and it's always convex, or well, should be convex, the better it is. That is where the optimum lies. There is even a measure for that, for this particular quality, and that is called the F1 score, which is the product of recall and precision 2 times divided by the sum. The sum is more forgiving than the product, means that it will always be close to 2, or more easily be close to 2 than the denominator is, because the product will only approach 1 if both recall and precision are high. So if you have a high F1 score, something of greater than maybe 0.65, it's a good value today, then you are actually working with a very competitive, very good system. It is due to this 2 here, also defined on a scale of 0 to 1. So in case of the recall and precision graph, you can even remove the graph itself and look directly at the F1 scores. However, F1 is only expressive for very good algorithms. For algorithms with average performance or with really bad performance, the F1 scores are close to 0 and not expressive. Then it's better to look at the curve. Okay, what is it for the recall, for the receiver operating characteristics? Well, usually it's shown as a square, so it is closed. This is the graph, by the way, that you have to provide in your lab experiments. There is a line going through the center of the receiver operating characteristics, and beyond the endpoints there are several possible developments. Let's draw 3 examples and say one classifier is here, another classifier is here, and the third classifier is here. In normal years we would do that interactively, and I would ask you what is the best curve of the 3, and I would silently hope for you saying, well, B is the best one, and hoping for nobody says A. But matter of fact, it is C. C is the best classifier. And why is that? We have the false positive rate on one axis. We have the true positives rate on the other. That means that if we go along the diagonal, for every classification step, there is a 50-50 chance that we have correctly classified or that we have wrongly classified. Such a classifier is exactly like flipping a coin and going to one of the 2 sides for the coin. That means it is worthless. It is essentially random. A is random. Okay, classifier B most of the time gives us the correct prediction. What is true in the ground truth is also true in the classifier, which is very nice. Whereas in comparison, C is almost ever wrong. For whatever thing you classify in the binary case, it will most of the time classify what is positive, what is relevant, as irrelevant, and the other way around. It's a really bad classifier. However, C can easily be inverted. And then it moves over and becomes a very good classifier. Let's denote it as C squared. And therefore, C is, in the event, practically the better classifier because it is more extreme. What we want to have, so, from such a classifier is we want to move it as far out as possible. And we do not care whether it's in the positive side or on the negative side. Somebody who is always wrong in the binary case is a very good predictor. That's the ROC curve. When you look at the ROC curve, then you always look for the 2 extremes. The further you are to the center, the less useful your classifier is. Well, now you might wonder, why is it a curve at all? I mean, I have one classifier and that's one dot, isn't it? So why do we have curves for recall and precision? These are mostly for different parameterizations of the classifiers, but also for different training, test, and validation set splits. So most of the time, you will not do one split, but you will do n splits of train, test, validation set. And then you will go over them one after the other, thus increasing the chance that the training set is not in some sense unfortunate, just representing one class or the other classes. If you follow a strategy to leave out certain classes, entire classes, then that scheme is called cross-validation. If you leave out always exactly in every round exactly one class, it is referred to as leave one out cross-validation, or LOOCV, as you can sometimes read in the papers. If you read that, you know that there were multiple experiments with different splits of training, test, and validation set, different not in terms of ratios, but in terms of elements, real elements that were chosen randomly. And it was always exactly one class that was left out and predicted in the test and validation set from all the other classes. And all classes were tried one after the other. Then it's leave one out cross-validation. Otherwise, it's just one other plain form of cross-validation, and there are plenty depending on the type of experiment that you have. Okay, last thing that I want to introduce is the mean average precision, because it's a popular measure in the world of deep learning. What you do there is that you define recall values such as 10%, 20%, up to 100%. Okay? And then you measure and summarize the average precision at those recall levels. And divide by the number of levels. That is the average precision. And if you do that over all the classes, then you end up with the mean average precision. So let's repeat it again. Mean average precision means define recall classes like linear split from 10 to 100%. See what precision you can gain at that recall level. As we said, you can always trade one for the other, recall for precision and precision for recall. Sum those up, divide by the number of classes n that you have, like 10 or 11 is very frequent. 11 is the more frequent one. It gives you the average precision, and if you repeat that over all classes, you have a mean of the average precision, which is very expressive because it tells you, it gives you an abbreviated form of the recall and precision graph. But it comes today with a drawback. The methods are so good that relevance values of 10, 20, 50, 60% are often simply irrelevant. You don't want to have these recalls included. And by including them, the mean average precision becomes artificially higher, which it shouldn't, of course. And therefore, recall levels should not be linearly distributed anymore, but only for the higher categories. However, if you do that, the drawback is that methods or results are not comparable to the results that we had, for example, 5 years ago. If we include them, comparing mean average precision values becomes a game of comparing the first or second element number after the comma, which is, of course, also not what a precision measure, a quality measure should actually express. Okay, so this is mean average precision, cross-validation, in particular leave one out, recall and precision graph, good if it's there. Receiver operating characteristics, good if it's there or there. Both of them can be automatically computed in a Jupyter notebook with a proper Python library. Both of them based on indicators that are themselves based on the confusion matrix. So, at the end of this very brief lecture on evaluation, I hope you understood what the confusion matrix is. It is about the binary case of relevant or not relevant for a single category. We have a set of measures, in particular the fundamental indicators recall, precision, fallout, interdependent ones, and the independent one with, most importantly, the F1 score, which is highly discriminative and sometimes even today too hard to be used, and mean average precision, which is sometimes too soft. And we also have two very nice and effective visualizations where you only look for extreme points and actually can forget the exact meaning of the indicators. I hope you enjoyed this video. If you have any questions, please post them in the forum. The link is given in the TU Information Systems, but as well at the end of this video. If you still have questions, get in contact with your lecturer and with your colleagues. Thank you very much.